All right, y'all, today we are going to expand on our knowledge of finding the area between two curves. We're going to do a warm-up that is related to like what we learned last class, and then we're going to kind of expand to something a little unique. All right, so warm-up, find the area between two curves that intersect at more than one point. All right, so I would love for you to put a rough sketch of this graph in your notes. Remember, a rough sketch means very quick sketch. And then we're going to figure out where these graphs intersect, and we're actually going to shade the region that we're trying to find. So this question says, find the area of the region between the graphs of f of x equals this function and g of x equals this function. All right, and before we find that area, I want you to pause the video, write the question in your notes, draw a quick sketch of the graph. That way you have everything you need to move on. Okay, so we're gonna shade the area of the region that we're trying to find. So let's do that really quick. We're trying to find the region that is bounded between the two functions. So this is a region that's captured between these two functions, and then this is a region that's captured between these two functions, and we need to find the area of both of these regions. It's going to be really helpful to label our graphs. So one way to know which graph is which is by using a calculator. Another way, like for this example, to know which graph is which is I can see that one of these graphs is a quadratic and one is a polynomial. So I'm just going to go ahead. We need to make sure we can recognize functions. So you can see that g of x is a quadratic, and that means it's a parabola, and it's a quadratic because you have x squared is the highest exponent. So I'm going to go ahead and mark the graph that is a parabola or a quadratic. That is g of x. So we need to be able to do this both with or without a calculator. All right, and then f of x is a cubic. You can see that the highest exponent is x cubed on the end there, and that is this function. Okay, so now that we've got both of our curves labeled, let's go back to remembering how to find the intersection of points without a calculator. Let's do this one without a calculator. We'll do the next ones but without a calculator, how do you find where these graphs intersect? We're going to need to find those intersection points, these intersection points, because that's like where our areas start and end, right? So we need to find those intersection points. How do you do that? You set the two functions equal to each other and then solve for x. So that's what we're going to do. We're going to set f of x equal to g of x. So we're going to say, okay, 14x plus x squared minus 2x cubed equals, and then g of x is x squared minus 4x. Cool. Then we solve. We have a polynomial and a quadratic. The best way to solve that is to set one side equal to 0 and then factor. So we're going to subtract the x squared, so minus x squared plus 4x minus x squared plus 4x, and we get 18x. The x squareds cancel, minus 2x cubed equals 0. All right, once you set it equal to 0, you factor to solve a polynomial. So we need to factor out, I can factor 2 and an x out, and we get 9 minus x squared equals 0. Oops, I said 3 because I'm already seeing something about that 9 minus x squared. You could also flip this, make it negative. I'm going to make the x squared positive. So how do I do that? I put a negative out here, and then I can turn, actually, no, sorry. I didn't want to do that. Forget what I just said. Well, we can flip it, or we can just like write the fully factored form, which is 2x 3 minus x, and then 3 plus x, right? Because we can factor using difference of squares, factor 9 minus x squared. Okay, so what do we get for our x's? What does x equal? let's do this in like a green. So for here, I'm going to go over here. X equals, for this one, we get x equals 0 for the x out in front. For this guy, we get x equals 3. And for this guy, x equals -3. So that's where these things intersect. So we can now say, okay, this boundary, this x right here is -3 for sure. Even though we could like probably just look at this one and see that, we have to know for sure. So that's how we check for sure. This one's 0. And then this one is the 3. So I'm going to like mark right here. That's where x equals 3. Okay, cool. Now that we have everything like set up on the graph, we are ready to find those areas. All right, so let's just remind ourselves of how to find area between two curves. The area between two curves equals the integral from a to b of your top function minus your bottom function with respect to x. Okay, so you can see if you look at this graph, we kind of got a weird situation happening. G of x is on top here, but then it's on bottom over here. So we're actually going to need two integrals. We're going to do two integrals. So I'm actually going to split this into different colors. That way I can like represent both integrals, but we're going to add up these areas using that top minus bottom concept, the integral of top minus bottom. Okay, so let's do our blue integral first, and I'll do that one in blue. So we're going to have the integral from, all right, for the blue area, the blue shaded region, we need to go from -3 to 0, right? So the integral from -3 to 0 of, and then what is my top function? My top function there is g of x. So I'm going to put my g of x function, x squared minus 4x, and then subtract, and then put my f of x function. Remember to put that f of x function in parentheses. And that was a little messy. Okay, with respect to x. So there's my blue shaded region. Then, because we have a second shaded region, we need to add. So plus, and then we're going to do the area of our green shaded region. So the integral from 0 this time to 3, right? The integral from 0 to 3. Use your x boundaries there always. And then my top function this time is f of x. It's my pink function. So we're going to do 14x plus x squared minus 2x cubed. And then minus my bottom function, which is my g of x, x squared minus 4x dx. Okay. So this is a huge, ugly integral. If you were going to solve this by hand, I would simplify the interiors of your integrals first. So for example, I would simplify this and simplify this before solving it by hand. But we're actually going to do this one on the calculator. So, and actually we did that yesterday. So you should be able to do this on the calculator. Make sure you get your parentheses right. Just a heads up, the calculator starts you off with like some extra parentheses. It always puts parentheses around this whole thing that's in the integrand. So you'll need a little bit of extra parentheses if you want to try to type this all in. And if you're going to check yourself, which I really want to encourage you to do on your own, type this into the calculator, you should get 81 as your answer. So if you add those two integrals, you should get 81 as your answer. All right, that was the warm up. Now let's do a little bit of a unique type of problem. Find the area between two curves expressed as a function of y instead of a function of x. All right, so again, I want you to write this problem in your notes. Draw a rough sketch of the graph. Let's read it really quick, and then I'll give you a second to write it all down. All right, example 3, horizontal rectangles or a y-axis approach. These are like different names for like what we're about to do. Find the area of the region bounded by graphs of All right, and then you may notice something immediately. We have x equals 3 minus y squared. That's a function defined in terms of x. It's x equals, not y equals. So that's what's really weird and unique about this problem. And then we have x equals y plus 1, another function defined in terms of x instead of y, right? Okay, now you can probably guess which one is which because it's still a similar situation where your linear function is going to be the straight line, but you can see your parabola is turned sideways, and that's because we have x equals instead of y equals. So really quick, you're going to draw this graph and then label your functions. So this one is your pink function. Oof, sorry y'all. This one's your pink function. That's like the quadratic function. X equals 3 minus y squared. And then the other one is your purple function. All right, go ahead and take a minute to draw these two graphs and also shade the area bounded by those two curves. Okay, so we've got everything set up now. Let's talk about how we need to do this type of problem. So you can tell that these functions are defined as y functions instead of x functions, like they're dependent on y. And so we're going to need, if we did this like a normal integral, let's suppose we did this like a normal integral really quick. Let's pretend we're going to find the intersection points on these in a second, but let's pretend that they actually, you know what? Yeah, let's just pretend that they intersect at -1 and then at 2. Okay, let's pretend this is where they intersect. If we were to do an integral with respect to x, so if we were going to do everything normal, here's what the integral that we just did last time was doing. It was saying, let me take little slivers of area. So let me take this little area, this little area, this little area, slivers of area, and let me add all those slivers of area up this way, like across on the x-axis in the x direction, right? We're going like along the x-axis. Let me add all those areas up until I've given you all of the areas added. That's what the integral does. The problem is if we did that, this chunk would be, that chunk would work normal. We have top is purple, bottom is pink for our like integral, top minus bottom. The issue with this is though, what do you do for this section? What do you do for this section? Because you don't have a top and bottom. That's all the pink function, right? There's no top bottom, like pink is top and bottom in that section from 2 to x equals 3, right? So this is why we're not going to use that same method. Instead, what we're going to do, and that was a bad idea, sorry y'all. Instead, what we're going to do is we're going to sum up areas in the y direction. So let me show you how that helps us. What if we sum up areas in the y direction? So instead, we like flip the way that we're going with our adding of areas, and we go this way. So we start low, and we add up areas high. But you would have like an infinite number of little slivers that you're adding the areas up on, or for. So why does that help us? Well, because if you do it that way, your function on top is always going to be the same, because instead of top now, you think of like rotating this. Instead of top, you're going to use right minus left. So we're going to use the right function minus the left function. So this, if you're going in the y direction, this pink function would be like your top function. Your right. Right equals top. And then the purple function would be your left function. Left equals bottom. So I'll show you kind of what we're doing. Instead of, basically, you're going to do the same thing. You're just using where you were using x's before, you're using y's, and vice versa. So here, instead of using from -1 to 3 or 2 or whatever, now we're going to use the y's. So this actually intersects right here at y equals -2. So we're going to use this y equals -2 as our boundary, our bottom boundary. And then we're going to use the top boundary will be this intersection point, and that's where y equals 1. So do you see how I'm like, instead of using x's, I'm thinking about doing this the same way, except flipping to y's. And instead of doing top minus bottom, we're going to do right minus left. Cool. How do you know that you're supposed to switch this like right minus left situation, like go to this type of problem? Because your functions are defined as x's instead of y's. Or because it will tell you to integrate like along the y-axis instead of the x-axis. Normally we integrate using the x-axis from point A to point B. Now we're integrating using the y-axis from point A to point B. Cool. And then top is on here, bottom's on here compared to the x-axis. But for the y-axis integration, we're doing right minus left. Okay, so let's write all this down. Let's kind of like summarize. For the y direction, we're going to say a equals the integral from, I'm going to actually say c to d, because it's not like the a to b. Let's call like the y ones c to d. If you want to like draw this, the integral from c to d. And then instead of f of x here, we're going to have a function of y with respect to y. Oops. We're going to have f of y minus g of y. Sorry, because remember the area needs to be right minus left with respect to y. And then please make sure that you note to yourself that this is right minus left. So it won't always be f of y. It's always going to be the right function minus the left function. Okay. That's like what f and g are. All right. So now let's actually do this problem. So we're going to do a equals the integral from, and then instead of a and b, we're going from y to y. So the bottom y, -2, to the top y, where they intersect, 1, -2 to 1. And then we're going to do the right function. My right function this time is my pink function. So that's going to be 3 minus y squared minus my left function, which is the purple function right here, is the left bound function. So it's going to be minus y plus 1 with respect to y instead of x, because now we're like integrating up the y-axis. We're adding up areas vertically instead of horizontally. Okay. Let's do this one by hand just to prove that we can do these by hand. So I really want y'all to understand that like you don't always have to use a calculator to solve these. So let's go ahead and simplify the inside of the integral. So equals the integral from -2 to 1 of, let's see, we have 3 minus y squared minus y minus 1. When I distribute that, simplify some more. The integral from -2 to 1 of, we have 3 minus 1. So we have 3 minus 1 is 2 minus y squared minus y dy. Cool. Let's go ahead and integrate that now. Let's integrate it. So I'm going to do this in a different color just to represent the fact that we have integrated. Let's do it in blue. Equals. All right. What is the integral of 2? With respect to y, it'll be 2y. The integral of -y squared is going to be -y cubed over 3. The integral of -y is -y squared over 2, right? And then we have boundaries. So evaluated from, sorry, let's do our little stick thingy. Evaluated from -2 to 1. All right, cool. Now all we have to do is plug in our top boundary. subtract, and then plug in our bottom boundary. So we have 2 parentheses 1 minus 1 cubed over 3 minus 1 squared over 2 minus, we have 2 negative 2 minus negative 2 cubed over 3 minus negative 2 squared over 2. Sweet. Now, if this was an FRQ, I would leave my answer in this form. I would just box this. So that would be your FRQ answer. If this was a multiple choice, you would need to actually evaluate this. So that means you'd have to simplify it all the way down. So this is your FRQ answer. And then if you want to try simplifying this by hand, that would be really, really good practice for the AP exam. And I can tell you what you'll get. If you simplify by hand, you'll get 9 over 2 after simplifying all the way down. So equals 9 over 2. This is your multiple choice answer. All right. That's it for notes for today. And I will make a couple more practice problem videos for y'all just to have some more examples. Cool. Good luck and do your best during practice.